Welcome back. I want to start out by doing another example, and I want to show you how you can use these double angle formulas that we just derived in the previous video to find different values. So let's say you are given cosine theta equals 3/5, or 3/5, and sine of theta is less than 0. And we're asked to use identities to find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. First, we need to figure out where cosine of theta exists. We know that if sine of theta is less than 0, that would have to be the third and fourth quadrants only. But cosine is positive, which means we also need to rule out any values that would make cosine negative. Cosine is positive in the first and fourth quadrants. So I can identify where the quadrant I'm looking for is going to be based on that information. The overlap is where cosine of theta is equal to 3/5. It's in the fourth quadrant. Now that I have identified which quadrant I need to use, I'm going to sketch cosine of theta equals 3/5 in the fourth quadrant. I know that my adjacent side is 3 and my hypotenuse is 5. That means I must have a 3, 4, 5 triangle. The hypotenuse is never negative, and 3 is in the positive direction, so that means the opposite side must be -4. Now let's find sine of 2 theta. Sine of 2 theta is going to be 2 sine of theta cosine of theta. I'll replace the sine of theta with the value I would get if I'm using theta to find sine of theta. That would be opposite over hypotenuse, which is -4/5. Cosine of theta, we already know, is 3/5. And I can find my answer. I have -8 times 3 is -24 over 25. Now let's look at cosine of 2 theta. Now there are a lot of different formulas. There's 3, so we can just pick one that we like. We could do, let's use cosine squared theta minus sine squared theta. That's just one of many, so don't feel that you must use that one. There's also 1 minus 2 sine squared theta and 2 cosine squared theta minus 1. So it doesn't matter which one you pick. They should all come out the same. We'll substitute the cosine value in, which is 3/5, and we'll square it, minus the sine of theta, which was -4/5, and we'll square that one as well, which gives me a 9/25 minus 16/25. That's equivalent to -7/25. Let's take a look at tangent of 2 theta. Remember from our derivation of tangent of 2 theta, the formula for this is 2 tangent of theta over 1 minus tangent squared of theta. And now I need to find tangent of theta. Remember that tangent of theta is found with opposite over adjacent, So that will be negative 4 over 3 divided by 1 minus negative 4 over 3 squared. And this gives me 2 times negative 4, which is negative 8/3, all divided by 1 minus 16/9. And I'm going to change this 1 to a 9 over 9 because I can. So I have 9 minus 16, which is negative 7/9. And remember, I can flip the second fraction over and multiply, which will give me a negative 8 over 3 times negative 9 over 7. And that will give, that doesn't reduce. Oh, yes, it does. It does. 1 and 3. So I'll have negative times a negative is a positive. 8 times 3 is 24 over 7. So that is the value for tangent of 2 theta. Is equal to 24/7. Now, you may be wondering, how could I find theta? Well, you take tan inverse of 2 theta. That would give you just the 2 theta. And then you would divide by 2, and that would give you the actual angle. So the angle is being doubled. That's why it's called a double angle formula. Next, we need to prove that cotangent x times sine of 2x equals 1 plus cosine of 2x. I'm going to work on the right-hand side for this one, and it's kind of up to you, depending on what you see as patterns, which one is easier. I first am going to replace my cosine of 2x with the rule that I created from the sum, which is that cosine of 2x is the same as cosine of x plus x. And so I'm going to rewrite this as 1 plus cosine x minus sine x times sine x. That means that I'll have 1 plus cosine squared x minus sine squared x. I'm then going to rewrite that as a replacement of 1 with the Pythagorean identity on the other side, which is sine squared x plus cosine squared x plus cosine squared x minus sine squared x gives me the ability to cross out the sine squared x's. At this point, I will have cosine squared x plus cosine squared x. I need to get a cotangent in here somewhere, and so I'm going to break these into pieces. I know that I have 2 cosine squared x. So I'm going to write this as 2 cosine x times cosine x. I'll give you a minute to think through that. Those are equivalent. Now, because I need a cotangent and I need a sine, I'm going to both divide and multiply by sine of x, which is the tricky part of this identity. So now I have a sine x in the numerator and denominator, which is equivalent to multiplying by 1. And now I can rewrite the whole thing as it appears on the left-hand side. But I'm going to move this 2 over in front of the sine x times cosine x, and I will have a cotangent x on the left times 2 sine x cosine x. This will simplify to the cotangent of x times sine of 2x. And so we have proven this as desired. This example 6, says write sine of 3x in terms of sine of x. This just means I have sine of x plus x plus x. So I need to think of how I might be able to rewrite that. That would be the same as saying sine of 2x plus x. And I know the formula for double angles, but I could also think of this as a sum, the sum formula, which would give me sine of 2x times cosine of x plus cosine of 2x sine of x. And then I could expand that out further. I know that the sine of 2x is 2 sine x cosine x times cosine x, plus I know that cosine of 2x is cosine x minus sine x times sine x. And that's multiplied to sine x. Simplifying here, I'll have 2 sine x times cosine x squared plus cosine squared x times sine x minus sine cubed x. So now we need to see if we can get rid of any of these cosines. We have cosine squared x in 2 places, and we're supposed to write this only in terms of sine. So if we look at our Pythagorean identity, remember sine squared x plus cosine squared x equals 1. So if I solve for cosine squared x, I'll have 1 minus sine squared x as the replacement, which will give me 2 sine x times 1 minus sine squared x plus, again, replacing cosine squared x with 1 minus sine squared x times sine x minus sine cubed x. If I distribute my signs, I'll get 2 sine x minus 2 sine cubed x plus sine x minus sine cubed x minus sine cubed x. And let's see how many like terms we have. We have a minus 2 sine cubed x. We have a minus 1 sine cubed x and another minus 1 sine cubed x. If I combine like terms, I have 3 sine of x's and I have negative 4 sine cubed x's.